We are CognoClick, and today we're going to walk you through the recommendation engine that we built for Amazon. Hello, my name is Julia Rod, and my primary role has been project manager for the team. CognoClick is comprised of 4 team members, and each team member has brought a unique mix of interdisciplinary skills to the table. Throughout the recommendation engine project, each team member has worn many hats and contributed to both the writing responsibilities and the programming responsibilities. Today, you're going to hear from each team member on various aspects of the project. The agenda for today's session is as follows. I'm going to walk you through the business opportunity facing Amazon and the solution that CognoClick ultimately came up with. Next, you're going to hear from Hemant, John, and Brian on the approach that the team took to build the recommendation engine, the results of various models behind the recommendation engine, including the dashboard and mobile application. You'll also see demos of the recommendation engine itself and the dashboard and mobile application. Lastly, I'm going to tie everything back together by sharing CognoClick's recommendations for Amazon and some of our reflections on lessons learned. Now, let's dive into the business opportunity facing Amazon. Amazon has always been a company that has put its customers first. Its mission statement reads as follows: to be the Earth's most customer-centric company, where customers can find and discover anything they might want to buy online, and endeavors to offer its customers the lowest possible prices. CognoClick knew that in order to develop a solution that would resonate with Amazon, it had to involve its customers. Since its inception over 25 years ago, Amazon has become an e-commerce and technology leader with customers all over the world. We know that Amazon is committed to creating a world-class customer experience, but that experience is in jeopardy. Today, Amazon is operating in an era of consumer choice. It needs to continue to find ways to target existing customers and attract new ones by presenting them with products that they are likely to buy. CognoClick recognized that customer reviews are a key data asset. They are what draw customers into Amazon's website in the first place, and they carry immense weight in a customer's purchase decision. For that reason, and because Amazon's reviews are so extensive, they give Amazon an edge over its competitors. CognoClick saw a big opportunity with Amazon's reviewers. They are a key customer segment and are already more engaged with Amazon's platform. By mining reviews for key information on customer preferences and sentiment, there's a big opportunity to increase product exposure with this segment. With this in mind, CognoClick will enhance the product recommendation experience for Amazon's reviewers. By developing more personalized recommendations, Amazon will experience the benefits of a more engaged reviewer base, and it will experience bottom line impacts, which are always helpful. The team recommended that it conduct this work in a pilot format, and a 10-week duration was agreed upon. The team also recognized that in order to be set up for success, it needed to hone in on data from a single product category, and that ended up being the electronics product category. By starting small, CognoClick felt that it would gain the feedback needed to help prepare for scaling across Amazon's other product categories. At the same time, this smaller scope would give Amazon the ability to better understand what it takes to manage this new program effectively. And now I'm going to hand things over to Hemant, who's going to kick off the approach and walk through how the team structured this recommendation engine.
Thanks, Julia. In order to help Amazon recognize and improve their recommendation experience, our team focused on identifying a variety of different tools and modeling techniques to help facilitate our proof of concept. Before we go into the detailed approach, I want to take a minute here to walk through our tech stack. We primarily considered tools and technologies that promote flexibility and scalability of our solution. We leverage Python as our primary programming language for data exploration, data visualization, and data modeling, as well as our dashboard build-out. We also use TensorFlow and Keras for our deep learning models, which we'll go through in the coming slides. In addition to using our personal laptops, our team also used Google Cloud to help facilitate some of the heavy lifting with data preparation and data modeling work in order to speed up our solution results. From a dashboard and mobile application standpoint, our team leveraged Dash, which is a Python framework designed for building web applications. In order to host our application, we used Heroku, which is a cloud platform primarily used to deploy and manage applications. And then from a source control standpoint, our team utilized GitHub for code management and Google Drive for document management. During our initial discovery phase, our team located Amazon product review data that was made publicly available by Amazon itself. The data consisted of over 130 million customer reviews from 1996 through 2014. As our team continued to research how best to source this data, we came across work that was completed by a professor at the University of California, San Diego, who had done extensive work with this data. He essentially partitioned and packaged the data into various product groupings, which enabled our team to focus on a singular category to build out our proof of concept. Our team chose to focus our efforts on analyzing review data from the electronics category within the broader data set. We examined 3 data sets, which consisted of the product review data, the product metadata, and the product question answer data. The product review data consisted of textual review data, data around how helpful the review was, and the 5-star product rating given by each reviewer. The product metadata consisted of product-specific elements such as product subcategories, product price, and the sales rank information for a particular product. The product question answer data consisted of questions and corresponding answers for various products. At a high level, when we decomposed the electronics review data, we found approximately 1.6 million customer reviews that were completed by over 192,000 reviewers across 63,000 unique products. The vast majority of the reviews in this category had a positive rating, and by positive we mean ratings of 4 or 5 on a scale of 5. And while we didn't have any web analytics data for this project, we believe there's immense value in capturing and analyzing this information to further enhance future iterations of this recommendation engine. As a natural next step, our team examined the underlying data to perform necessary data cleansing, data transformation, and any sort of feature engineering tasks to facilitate our modeling work. Our goal was to flatten the data such that it was easily interpretable, and we also wanted to make sure that the data we were working with was complete, and in cases where it wasn't, we either excluded the variable or imputed the variable where appropriate. We essentially divided the data into 3 groups, the first being reviewer features, the second being product features, and the third being review text features. For the reviewer features, our team aggregated various data elements at the reviewer level. For example, we computed summary statistics for variables like product price, product rating, and length of time between reviews for each reviewer. Our goal was to understand user behavior and the inherent variability at the reviewer level. For the product features, our team aggregated various data elements at the product level, similar to what we did for the reviewer features. Our goal here was to understand product variability relative to reviewer variability. And then for the review text features, our team employed natural language processing techniques on the textual review data to generate features for product recommendations. We focused on removing words such as the or and or any other common filler words in order to generate a reviews corpora at the reviewer level and at the product level, which enabled our team to identify product nuances that may not have been otherwise captured through metadata features alone. Now I'll hand things over to Brian, who will provide background on recommendation engines.
Thanks, Amat. And now we're going to talk a bit about what recommendation engines are. And we'll start off with a quote by Julian Macaulay, who is a well-known professor at the University of California, San Diego, and an expert on recommendation systems. He says, "The basic task of a recommender system is to suggest relevant items to users based on their opinions, context, and behavior." And this is exactly the approach that we took at CognoClick to identify the most relevant products for Amazon users to ultimately increase the purchasing rates and revenue for Amazon itself. And we accomplished this via a number of different approaches. Recommender systems can be performed via a number of different types or methods, but the most common methods are content-based, collaborative-based, or a hybrid of both of those options. Content-based methods effectively try to identify similar products or products that are similar to people's activity, whereas a collaborative filtering method has two discrete methods, which are typically model-based, which is usually trying to find similar products that are near a distance or a product for a user, typically following similar item to item based on two users or two users' personal preferences. A model-based method, conversely, is trying to predict the rating or relevance for an unrated item for a user, maybe something that somebody's never seen before. And then a hybrid model tries to mix both of those approaches together. Now, we considered many of these different approaches, and to assess what makes the most sense of the approach for Amazon's user base and product base. Content-based filtering attempts to identify similar products by looking at its metadata or information that defines it and who has reviewed those information. Some of the details could be looking at the metadata, such as the title description or the content of the reviews that Julia has spoken about before. Collaborative filtering, however, leverages user behavior to make recommendations. Collaborative filtering learns what a user likes, reviews, or watches, depending on whether it's an e-commerce movie site or product site. And based on those interactions or reviews, it recommends products that would be similar to those the user liked, reviewed, or watched. With this approach, collaborative filtering can recommend new items that a user has not been exposed to before, but other similar users may have interacted with. Now, collaborative filtering has its benefits. However, one of the drawbacks is it suffers from what's called the cold start problem. And the cold start problem is an issue where a recommendation engine, specifically a collaborative filtering recommendation engine, can't recommend a new product if the user has not interacted with it in the past. However, content-based filtering does not suffer from this problem. And if you think about why that is, uh, products are independent of people. So two similar products can be recommended to two different users, even if they haven't interacted with them. However, if you're basing collaborative filtering on a user's behavior and you have no details of a user's behavior, then you can't recommend anything to them. That's often why a hybrid can be a good medium between these two options to account for both new or cold start problems. In the end, a hybrid method was selected as the best approach for CognoClick, and you can see here an example, a simplified example of how a hybrid works, where two recommender engines are executed over a set of data, and then the hybrid consolidates the results, increasing the likelihood of relevant products for the end user. And as we mentioned previously, the hybrid model is going to give better output and relevance to the user, but it offers additional benefits such as better performance, better flexibility, and better scalability, which allows us to modify the approach, swap in one or more additional engines based on different types of products, different users, or changes in the ecosystem that Amazon might be changing or enhancing as their products and company evolves. And now I'm going to turn it over to John to discuss the modeling approach.
Thanks, Brian. Over the course of this project, the team has spent a lot of time researching and discussing various modeling approaches to best solve the problem at hand and enable the team to operate efficiently. The primary objective in being mindful of our modeling approach is to yield the most relevant recommendations for Amazon's reviewers. Although it is possible to train and test the accuracy of product recommendations using the product ratings, the relevance of the actual recommendations themselves can be difficult to determine without end-user feedback. Said differently, Without the ability to test the recommendations on the end users, it is very difficult to completely confirm or deny that a recommendation is in fact valid. I, as a data scientist, may have a hard time appreciating the nuanced relationships in recommending microphone cords or cables. Understanding this limitation, the team set out to provide as much coverage as possible should a model or maybe a collection of models provide an answer that could greatly benefit Amazon reviewers. There are numerous cited examples, including the Netflix recommendation engine challenge, where the final solution was thousands of models. Fortunately, recommendation systems often benefit greatly from an increased number of models that are incorporated into the final solution. So as such, we realized that the best modeling approach would be one that provided the team the most flexibility and agility to develop and iterate through multiple models and techniques. Unfortunately, we did not have time during this proof of concept phase of the project to build out thousands of models to support the revamped recommendation engine. To encourage rapid and agile development cycles and set the team up to build multiple models, the team embarked on a development journey that has been dubbed, for the sake of simplicity, Phase 1 build and Phase 2 build. This development journey is outlined by the graphic on the right. The Phase 1 build involved creating prototypes of the models that were prioritized during the due diligence phase. Phase 1 build is represented by that red box on the graphic. Phase 1 provided the team with some insights into what methods had the most promise and what methods could be or would be potentially hamstrung by technology and scaling issues. It also provided the team with valuable outputs that could be used as inputs into Phase 2. During the Phase 2 build, the CognoClick team leveraged the learnings, outputs, and findings from the Phase 1 build to generate model enhancements. Phase 2 involves scaling the models beyond the limited samples used in prototyping. It's represented by the yellow box and the graphic on the right-hand side of the slide. Based on our research and due diligence, we identified and prioritized 3 key models for the proof of concept. The 3 models that were identified were called the baseline model, which is that blue box that it is located in both Phase 1 and Phase 2. The review text model, represented by the gray box, and the outputs in that long rectangular box in between the two, and the deep learning model. The deep learning model being the green box all the way to the right. The baseline model leverages product ratings data only. The review text model uses features derived from the review text, and the deep learning model uses metadata and text features from both the reviewers and the products. The outputs from Phase 1, especially those of the review text, are used as inputs or the starting point for Phase 2. We'll go into more detail on each of these models in some of the following slides. In some of these next models is that on a data set, the scale and the size of the reviewer data that we were working with, we had a lot of memory and a lot of system limitations that we ran into. Fortunately, we were able to take advantage of some of the cloud resources that are available to students and to first-time users of Google Cloud Platform. So we were able to spin up a server and execute some of the baseline model and some of the review text model. But ultimately, we did run into serious memory limitations there, even after maximizing the available resources on Google Cloud Platform, which I think is like 650 gigabytes of RAM and 24 processors for an individual not associated with a corporation. So we tapped those out and then ran out of credits. So we would recommend that if this does get revisited, consider either scaling up an even larger machine than that, or breaking the problem into smaller and smaller pieces and processing it at a lower and lower level. With that, we'll jump into the actual model results. In determining how to best build a baseline model, only collaborative filtering methods were considered, since these methods offer a greater variety and recommendations to a user. Both memory-based and model-based methods for collaborative filtering were built in to help determine what the best baseline model was. With the broader goal of wanting to leverage both metadata and text features in the final model, it was clear that the purpose of the baseline model was to serve as the point of comparison, as this was not necessarily an option for the baseline model. The baseline model would help to show the value in adding more complex features and leveraging more complex modeling techniques such as deep learning. Therefore, rather than going and manually building out an implementation from scratch, the Python surprise package was leveraged to build the baseline model. The Python surprise package is implemented through scikit-learn. It has the advantage of offering many recommendation algorithms and various features such as cross-validation and parameter tuning, and it's extremely accessible. This enabled the team to devote more time on the natural language processing as well as the deep learning model. Moreover, the surprise package, it allowed for us to have a model-based approach to be considered the baseline model. The algorithm that was selected is the Singular Vector Decomposition Model, or SVD, and it's described in detail in the final paper. The actual algorithm itself decomposes the user item matrix in an attempt to predict ratings for products for that user when the user has not rated that product. Therefore, it's model-based. One of the interesting things that we had learned about this was that it is, because of the nature of sparse matrices, it is extremely memory intensive to perform these calculations. So if you take the entire matrix of every user and every item, you have an extremely sparse matrix, as there's a number of users that have not had reviews on a number of items. So you have a lot of blanks. This takes up space, takes up memory, and ultimately is very computationally expensive. So one of the things that we were able to do was to break the problem into smaller and smaller pieces, leveraging the outputs from the next model to be covered here, which is the reviewed text model. We ran it cluster by cluster, breaking the user groups into smaller and smaller pieces such that they were able to be further calculated with the existing cloud resources that we were able to pull together. So while we didn't get results for the entire set because we burned through all of our credits after executing cluster 0 and cluster 1, we were able to get a set of results for the users in cluster 0 and cluster 1. The model was ultimately put on the shelf because, again, this was considered the baseline model, and as we explored and did the prototyping, we found that the deep learning model had significantly more promise and was way outscoring the SVD model in all of the benchmarks and comparisons. So ultimately, it was just used as a benchmarking tool and put on the shelf. The review text model was substantially built during the phase 1 build portion of this project. The intention of this model was to try to leverage the large, massive, rich corpora of text available to us as part of the original data set. From that data set, we would have to mine and cleanse and purge a significant portion of those reviews into distinct corpora so that they could be further processed and modeled. There are two different perspectives that we can really think about the data that was aggregated into different corpora. So we created one from the perspective of a reviewer and all the other similar reviewers. So the corpora was on a reviewer basis. And then there's another set or another perspective to think about, and that is from a product perspective. So the reviewers are ultimately rating the products. When we do the grouping of the text data by product, are we hearing and seeing similar things being said about the products by different reviewers? Once the corpora were organized into those two different groups on a reviewer basis and product basis, we were able to then transform that information into TF-IDF matrices, or term frequency inverse document frequencies. This method, or TF-IDF, is something that is commonly used in natural language processing that helps to measure the uniqueness and importance of a word and term in a corpora. As part of the k-means clustering implementation that was performed, we elected k to be equal to 10, so we ended up with 10 different clusters. But what we quickly found was that doing this analysis on the full electronics dataset became too computationally expensive. We quickly whittled the set down closer to the camera and photos dataset, which was then able to be graphically represented as you can see there. The camera and photos dataset is what we largely used from that point on to ensure that we had the resources available to process the information. We were able to successfully generate the TF-IDF matrices for all of the electronics datas and all of the camera and photo sets, as well as we were able to cluster every group or every individual and every product into one of the 10 clusters. What we had found was the clusters seemed to be more effective at identifying similar products than similar reviewers, which, when you take a step back and think about it for a moment, may make sense, as all the reviewers tend to, when they're writing reviews about products, they tend to write similar things about similar products. That seems to add up. It was a little bit harder to get at the core of who and with the personal elements that are associated with every individual from the natural language. So that was not as effective in that regard as we would have hoped. But nonetheless, the outputs did prove to be extremely valuable for two reasons. One, we now had smaller subgroupings that were available for us to break our problems down even further. So if we wanted to revisit the baseline model, we could take it and chunk it cluster by cluster and perform these different operations that we're performing, like the SVD, as well as now the opportunity to leverage those same inputs for deep learning. So we could take those TF-IDF matrices to feed the autoencoder models.
Thanks, John. So now we're going to talk about our deep learning model. And before we get into the details, let's first level set by defining what deep learning is. Deep learning is a specific subfield of machine learning, and it's a new take on learning representations from data that puts an emphasis on learning successive layers of increasingly meaningful representations. So what does that actually mean? It's an idea of creating these layered representations called neural networks that are literally layers stacked on top of each other, which looks like a network. And those layers allow for increasing complexity to be modeled and represented by the technology that's not as easily performed with traditional machine learning techniques. And this is the primary reason we took this approach, given that the Amazon product and reviewer data is naturally complex and has a depth to it that is more challenging to capture or model using traditional machine learning approaches. So the deep learning approach helped us look at different model structures. It also helped us to leverage both content and collaborative filtering model techniques. Given that deep learning was able to handle both metadata and textual features in a model, we could assess and test the effectiveness of the deep learning model to determine what makes the most sense and what model might yield the highest relevant products for the user. And we did this in a very structured, phased approach where we started with a very simple deep learning model where we were looking at the combinations of reviewers and products and ratings and training a model that attempted to identify what a reviewer would rate a product based on the interactions they had with other products as well as the interaction that other users had with the same or similar products. And then we ultimately, after getting reasonable results with those initial models, we scaled it up to include the metadata, textual content, and other information that was available in the Amazon data. Now, even though the models got increasingly more complex and difficult, the deep learning models did not suffer from the big data challenge that often requires distributed computing to perform. And we were able to perform all the analysis for the deep learning models on a single computer, which displays the breadth and flexibility of this approach to help Amazon scale with their products across millions of different of users and millions of different of products. So let's take a quick look and jump into a demo here to see what this actually means and what this looks like for Amazon. So we're going to take a look at a web representation or a web product that we built that leverages the models that we developed. And these are the two optimal models that were trained and developed as part of the pilot process here. And similar to what we've been talking about, we have two separate models. We have a collaborative filtering model on the left and a content filtering model on the right. And this has been developed and set up in a way that any user could come into Amazon and look for recommendations. So the web application that we've developed randomly selects a reviewer, then predicts the products that are likely the most relevant to them based on their past reviews. Or similarly, when you click on a new product or a person comes in with no user profile, clicks on a new product, we're going to show them similar products based on the product that they collect. And we can do this using the two buttons here. So first, we'll start by clicking on a random reviewer. And when we do so, we are going to get a random reviewer ID. And that ID is the internal identifier for Amazon and how they track their reviews. Now, to get the collaborative predictions, we have to look at all of the different products that have been reviewed by that reviewer, as well as the multitude of products that exist. And there's nearly 200,000 users in the electronics category, as well as roughly 60,000 products in the corpus of electronics. So we're looking at a huge volume, just under 2 million combinations of users and products that the model is quickly predicting what is going to be the most relevant for that reviewer. And currently it's doing this on the fly, so it's doing the predictions as we wait. Now this can be pre-computed to effectively streamline the process, which is an often a technique that is preferred to the on-demand training that we're doing here. But now you can see that the results come back, and we're looking at that this specific reviewer, it's rated. We have some predicted ratings here, so all these products look like they're rated a 5, so that's likely why they're showing up here as the top rated items. So based on the products that this reviewer has previously reviewed, these are additional products that they've never reviewed. So we're predicting the rating based on their past reviews. And we're using all the different metadata and context you see here. And you can see here that a lot of these are very similar. So we're looking at TV mounts. We're looking at, it looks like a camera, shutter release, a battery, probably for a camera, another battery, maybe a different camera, power adapter for a camcorder. So we're seeing a lot of common products here, and that's good. That means our engine, our recommendation engine is working. That's based on the user's preference that these products are being returned based on what they've looked at before. So now it looks like this person does a lot of camera and photos, so that's interesting. So a lot of the details are going to be relevant for that specific user. However, if we go back and try a different user, we should get something entirely different, assuming that that reviewer has a different taste or a different preference. So let's get one more reviewer. And we get, now we can see we get a new reviewer ID. So the number's changed compared to the last one we had. So let's go ahead and select the predictions. And again, because the model is training on the fly, it's going to take about 30 seconds here, similar to the last run where the model is going through and predicting the ratings for all of the different products that this reviewer has never seen. And once that comes back, it'll show us the products again in sort order by the predicted ratings. And if you think about where this would be used, this would typically be used on the landing page of Amazon.com. So when a user comes into the site and they haven't clicked on anything, but we want to give some relevant products to that reviewer or to that user as they enter the site, this is commonly displayed on the bottom of the page, something that might pique their interest based on previous um, reviews and purchases. Okay, so this reviewer comes back, and now we can see here that we have new products coming up. So it looks like we have a portable speaker, portable Bluetooth speaker. Pretty cool. I think I like that. We have some hard drives. We have some HD video cameras, some more hard drives, cables, accessories, some more audio cables, digital audio cables, and some stereo digital equipment. So it looks like we have a lot of audio equipment, similar to the The last reviewer, where we were primarily looking at um, photo type accessories, it looks like this reviewer likes audio, um, speakers, and hard drives. So maybe they are someone who does their own recordings or modifies audios and creates tracks. So pretty interesting there that we're getting some pretty similar. All right. So now that we've tested two different reviewers, let's take a look at content filtering, where we're just going to look at products. So let's first get a random product. So I can click here and get a random product. So this is the one of the roughly 60,000 products that exist in the Amazon electronics corpus. I can see here that it's a 27-inch LED monitor, $200 monitor, and it's in computers and accessories. So I want to see some similar products to this. If I come into Amazon and I click on this, I want to see similar options. And if I do that, lo and behold, I start getting some similar products. The most similar product is another monitor, a 24-inch LED monitor, almost the same as the ViewSonic. But I'm also seeing some mix of cameras and photos, as well as other monitors that we see here. So we're getting a little bit of mix for this specific product, and it could be that the reviewers that purchase these products tend to buy similar camera and monitors. So let's get another random product. Let's keep going. Let's look for, let's just keep clicking around until we get something very different. And oh, there we go, an iPod. That's kind of interesting. Let's see what's similar to the iPod. Oh, interesting. The most similar to the iPod is a portable CD player. I guess if you're looking at an old iPod, then an old CD player makes sense. An MP3 player, that's interesting as well. UPS battery, signal transfer, another portable speaker, Bluetooth speaker. Looks like a knockoff or an iPod. Maybe, oh, that's an iPod case. A case for a eSling, which is a DVD player similar to the top. So we're seeing some similar products. That looks pretty good. Let's do one more just to round out the. Let's do something maybe we haven't seen before. Um, let's take a look at. Let's get some. Here we go. Internal Bluetooth component. So let's see what's similar to that. Oh, okay, awesome. So we get some processors, and we're getting some memory. We're getting some fans. We're getting aluminum thermal compound, which is required to mount CPUs. So you can see here, this is working really well. We're getting all different components. So if you were a reviewer that was coming into Amazon looking for similar products to what we see here, I think you'd be pretty happy with the recommendations that are coming out of our engine. And now I'm going to turn it back over to John, who will talk a bit more about ensembling.
Upon completion of all of the individual models, we wanted to take a look or try our hand at doing some kind of an ensemble. So what we were able to do was to put together some kind of quick and dirty ensemble approach that really leverages the wisdom of the crowd here. The ensemble model takes the outputs from the baseline model, which, as a reminder, we were only able to get for clusters 0 and cluster 1. We then combine that with the outputs from the review text model. In this context, it is the average rating for an item provided by a cluster. So for cluster 0, for the camera lens in this graphic that you can see on the right, the average rating for that cluster was 4.44 for that item. That is then the predicted value for every single member of that cluster. Then we take the output of the deep learning model, the predicted rating from that deep learning model, and average it together with the other two outputs to produce the ensembled rating. This is a high-level and heuristic-based approach to ensembling these results. There's a lot of opportunity to continue to refine this approach. We just wanted to get something out there to give it a shot and see how it performed. Overall, it seemed to make sense. Maybe not so much that we would want to water down the results of something as powerful as the deep learning model. So we'll kind of put this one again to the side and revisit it at another date.
Thanks, John. Our team's focus centered around creating an improved recommendation experience, but we also wanted to create a dashboard and mobile application that would allow various teams at Amazon to consume and interpret our modeled recommendations. We had some limitations around data availability, so we limited our scope to product recommendations versus any sort of operational reporting for this dashboard. We leveraged Dash to build our application, which enabled us to use Python code we had already created throughout our data exploration and model building phases to help create a reactive, web-based application. With Dash, we're able to create an application that's versatile and portable across web frameworks, which essentially allows easy integration into Amazon's enterprise web framework. One of the key benefits of using Dash was having the flexibility to control virtually all customization versus having cookie cutter settings created by an out-of-the-box solution. So what I'll do now is walk you guys through a live demo of our dashboard and talk through some of the capabilities we were able to build for our POC. The dashboard you're currently seeing on my screen is hosted using Heroku's cloud platform. This exact view can also be used through a mobile phone. The dashboard is broken down in two parts. The top portion reflects overall product demand, and the bottom portion reflects rank-ordered product recommendations for a given product or a given user. The overall product demand visual captures the top 10 most popular products within the electronics category. When you hover over a given product, you're able to see additional information relative to that product, such as the number of reviews, the product price, and the product subcategories for that product. Moving down towards the bottom of the dashboard, we have two tables that capture recommendations at the product level and at the user level. These recommendations represent results from the deep learning content base and collaborative filtering models. The Product Recommendations tab illustrates the top 10 rank-ordered similar products to a given product, and similarly, the User Recommendations tab illustrates the top 10 rank-ordered similar products for a given user. Looking all the way towards the left of the table, you can see the first two columns indicate the original product ID and product name, and then the next two columns indicate the rank and the recommended product based on our model output. The remaining columns provide additional metadata around the recommended product, things like product subcategories, product price, the number of reviews, average rating, and a URL that points to an image for the recommended product. The User Recommendations tab follows a similar layout, but instead of the original product ID, we have the reviewer ID, as you can see here on the left. The dashboard has reactive filtering, which allows a user to easily filter across columns they see fit. So let's say the original product contains Sony, and we want to see products less than $15. As you can see, the table dynamically changes and provides the end user with contextual information related to the original product and filters they applied. Overall, the dashboard provides a deeper understanding of recommended products for a given product. Now I'll hand things over to Julia, who will provide concluding thoughts and recommendations.
I'm now going to take a step back and walk you through the recommendations the team has for Amazon, as well as reflect on the project as a whole. While the team was successful in building a recommendation engine, there are extra components that are needed for Amazon to take full advantage of the revamped product recommendations. The team has divided its recommendations into a Phase 1 and Phase 2. Phase 1 is all about getting the CognoClick product recommendations into production and establishing a foundation for Amazon. Phase 2 is focused on enhancing those recommendations in order to maximize revenue. There are 4 steps within the Phase 1 recommendations. First, Amazon must establish a cloud infrastructure. This cloud infrastructure will allow Amazon to fully support all the data processing and modeling that is needed to generate the recommendations. More importantly, the cloud infrastructure will allow Amazon to integrate the CognoClick recommendations into Amazon's existing technology stack and website. These recommendations need to be able to handle new users and new products. So this is a really important step in that process. Next, Amazon should launch the CognoClick product recommendations from the hybrid deep learning model into production as is. There are several enhancements that could be made to the current product recommendations, but those can all be addressed in the phase 2 approach. Amazon should start using the dashboard and mobile application to really understand the product recommendations. The CognoClick team recognizes the limitations of its current version of the dashboard and mobile application, which is why it recommends that Amazon establish some level of baseline results reporting to understand the impact of this program. This initial feedback will help Amazon to prepare for phase 2 enhancements and identify which items should be addressed first. The phase 2 recommendations are divided into 2 different groups. The first line is all about enhancing the relevancy and accuracy of the recommendations, while the bottom line is about scaling the recommendations through other avenues. These recommendations are not listed in any particular order, but Amazon should first implement the top line items before moving on to the bottom line items. The first item listed is establish a strategy for model retraining. In order to make sure that the recommendations are as accurate as possible, Amazon needs to consider how and when it will generate recommendations for new users, new products, and new activity. One consideration is to stream data based on user activity on the website in order to get real-time recommendations, which will allow Amazon to keep pace with its ever-changing product and user base. In addition, Amazon needs to consider some potential model enhancements. The team was cut short on its ensemble approach, so this is one avenue that Amazon could consider, as is creating new features for the model, such as text features from the product description text. Model retraining is such a critical aspect of this program, and it will help to ensure that the product recommendations remain an asset. The next item is to gain feedback from end users. The team built what it considered to be good recommendations, but end users are the true test of relevant recommendations. The team recommends that Amazon utilize an approach like interleaving or A/B testing to allow end users to pick or vote which recommendations resonate most with them. This type of feedback will provide Amazon with direction on potential areas of improvement that may be needed. Furthermore, Amazon should seek to incorporate web analytics data. Having access to web analytics data will allow for attributing sales back to the CognoClick recommendations and provide insight into things like product placement on the website. What's more, the web analytics data also presents a unique opportunity for the product recommendations themselves. With this type of data, the team will be able to incorporate things like product clicks or views into their recommendations, which could help develop more nuanced recommendations. This kind of data also opens the doors up to serving customers beyond just reviewers, since success events like a product purchase are not criteria for inclusion or exclusion into the program. With expansion on the mind, Amazon should definitely enhance its current version of the dashboard and mobile application to help manage the success and impact of this program. Adding in the web analytics data could be of great value for results reporting. Once Amazon has taken its current electronics recommendations to the next level, the next logical step is to expand those recommendations to other product categories. CognoClick recommends that expansion be done in a phased or incremental approach in order to mitigate impacts to the customer experience. Once expansion to other product categories have occurred, another next level enhancement is to expand to all customers, regardless if they have made a purchase and written a review. This expansion can occur simultaneously with the product expansion, but it is important for Amazon to leverage its foundation to develop more personalized recommendations for all customers. By implementing these phase 1 and phase 2 enhancements, Amazon will be better able to serve its customers. In reflecting on this project as a whole, the team has many takeaways. First, there were several project accomplishments that should be recognized. The team utilized a diverse technology stack. This meant that the team was able to deliver a solution that allows Amazon to stay on the cutting edge, but it also afforded the team with greater creativity throughout the development process. Next, the team took full advantage of an agile approach to build its revamped product recommendations. By constantly inspecting and adapting, the team was able to enhance the overall models built and drive continuous progress. It allowed the team to truly deliver a best-in-class recommendation engine. The team saw great success with the deep learning approach. This approach allowed the team to meet its goal of incorporating both metadata and text features into the product recommendations. It also meant that the team was not delivering Amazon a solution that is going to go stale right away. AI is all the craze right now, and Amazon has a property that will be able to grow with it. Furthermore, the team was able to see the benefits of a hybrid model. This type of model is able to develop more personalized recommendations and recommend products that are not just based on what a user has bought in the past. It also gives Amazon the ability to incorporate new users and products, which is essential. The team had the ability to learn new technologies throughout this project. One of those technologies was Dash, which was used to build the dashboard and mobile application. The team was able to see the benefits of this tool right away and easily incorporate it into its code base. By not building an application from scratch, Amazon is also in a position to better support this tool over time. Lastly, the team generated many ideas for future improvements. The team left no stone unturned, but it still identified several enhancements that could make the recommendations even more effective. This result is a testament of the team's focus on strategy and long-term success. In focusing on team wins, the team fully leveraged each team member's unique skills and experiences to drive progress. The diversity present allowed for a comprehensive solution to be delivered, but it also meant that each team member was able to chip in and help out when needed. Despite having unique skills and experiences, the team was fully committed to delivering above and beyond project goals, which meant that the team pushed itself until the very end, and the solution delivered was the best that it could be within the time allotted. Because the team challenged itself in the technologies and approaches considered, there was strong leadership and a good teamwork all around to make sure that milestones were hit. The team was very proud of what it was able to deliver in the end. That being said, there are some areas for improvement around the solution delivered. First, getting access to web analytics data would greatly enhance the product recommendations and allow for wider appeal. Second, getting end-user feedback on the models built would help to confirm the direction the team went for model building, but at the same time identify enhancements. End-user feedback is so critical to the success of any recommendation engine that the team would have liked this kind of access during the pilot. Lastly, the team could have benefited from a more robust cloud environment. While a cloud environment was leveraged when necessary, the team was limited in the resources it had available. Having a robust cloud environment is needed to fully support all the complex pre-processing, data preparation, and modeling activities behind the recommendation engine. As a whole, the team was able to work effectively together, leverage each other's unique strengths, and challenge itself in many ways to deliver a cutting-edge recommendation engine for Amazon's reviewers. We hope that Amazon is able to consider the Phase 1 and Phase 2 recommendations that have been shared to take full advantage of the recommendation engine and continue to deliver a world-class customer experience. Thank you.